So hello students. So now we'll start a new chapter that belongs from states of matter. Okay. So first let us discuss about gaseous state. Okay, state of matter. So first one, that is gaseous state. Gaseous state. You know, in your periodic table only few elements exist in the form of gases. Okay, so there are basically 11 elements exist in the form of gases. So first one, that is hydrogen and oxygen, nitrogen, diatomic gases, oxygen, nitrogen, and chlorine. That clear? And all the noble gases, starting from helium to all the noble gases. Okay, all the noble gases means helium, neon, argon, krypton, and xenon and radon. Okay, xenon and radon. So how many elements you see? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So these are exist in the form of gases. So gaseous state, one of the physical state. You might have gone through regarding this gaseous state in your previous classes. So right now, without wastage of time, let us discuss the characteristic properties of gases. Okay. So first one, that is characteristic properties of gases. Characteristic properties of gases. So first one, that is gases have no definite shape and volume. First point, gases have no definite shape and volume, and their shape and volume depends upon the container in which they are kept. Okay, so the shape and volume of gases depends on the shape of the container in which they are taken. Next point, gases have low density. The density, that is mass per unit volume, and you know gas molecules are very away from each other, so they occupy larger volume. So once volume is larger, so density becomes less. So they have low density as compared to that of liquid and gases, that of solid and gases. Okay, next, very important, that is intermolecular force. Very negligible force of attraction is there. Okay, so gas molecules correspond to very negligible force of attraction. So gas molecules have very negligible force of attraction. Next, diffusion. Diffusion means intermixing. So since molecules are very away from each other, they can intermix with themselves. Okay, so diffusion, gases have, they can they can easily diffused with each other. Okay. Next, compressibility. Since molecules are high distance apart from each other, so by applying pressure they can be compressed. Okay. The poses gases are compressible in nature. Then what about pressure? The exact pressure with respect to all directions. Okay, so gas molecules exact pressure in all directions. Okay, so these are few general characteristic properties of gases. And regarding measurable properties of gases, you know, the gases correspond to a particular temperature, pressure, volume and mass in the form of a number of moles also. Okay, so these are the important characteristics of gases. Let us proceed through very important topic, that is gas laws. Okay, so first gas law need to discuss, very important, that is gas laws. So first one, that is Boyle's law. Boyle's law, let us write down its statement first. Statement: at constant temperature, the volume of a given mass of gas is inversely proportional to the pressure. Okay, so mathematically volume is inversely proportional to pressure. V is inversely proportional to P. So provided temperature T, that is equal to constant, and mass of gas is also constant, that means number of moles N is also constant, mass in terms of number of moles. Okay, so this is the mathematical statement of Boyle's law. So if I go on solving, that V is equal to some constant K upon P, is that clear? So that implies PV, that is equal to K at constant temperature. This is the Boyle's equation. Clear? So PV is equal to K means, that means P1 V1 is equal to P2 V2, that is equal to P3 V3 is equal to K. So this will product of a pressure and volume always being constant, that is, you can say, that is at constant temperature for the given mass of a gas, the product of pressure and volume is constant. This is Boyle's law. Okay. Suppose a system is at state A, this one, gas, it is in state A, let's say, it undergoes change by Boyle's law. Change by Boyle's law. This one is another state, that is state B. That clear? So here let pressure P1, volume V1, temperature constant, let's say it is T, and mass of gas constant, that is M. Clear? Change by Boyle's law means pressure changes to P2, volume V2, temperature again remains same T, and N are constant. Then by Boyle's law I can write over here change by Boyle's law, that is P1 V1 is equal to P2 V2. That is equal to always P1 V1 is equal to P2 V2. Is that clear? Because if you apply here Boyle's law, that is V1 is inversely proportional to P1. So that implies P1 V1 that is equal to K. Is that clear? So here since temperature and mass of gas remains constant, again you can get V2 is inversely proportional to 1 by P2. So sorry, V2 is inversely proportional to P2. So P2 V2 that is equal to K. So overally we can get P1 V1 is equal to P2 V2 always remains same. That will be coming out as a constant. Okay. So from Boyle's law, okay. So from Boyle's law, what we have got? V is inversely proportional to P. Okay, so that implies V that is equal to K upon P. Am I right? Okay. Now, if I consider density D that is equal to mass per unit volume. So what is the value of V over here? So mass upon V you can write K upon P. So that will be equal to P M upon K. Okay. So mass of gas constant. So this one is constant for a given mass of a gas always I am saying, and this K is also constant. So from this equation I can write D that is equal to, this ratio becomes let's say K dash into P. Is that clear? So from this relation D is direct proportional to P. Matlab density of gas is direct proportional to the pressure. So I can write over here hence the Boyle's law may also stated as for the given mass of a gas, the density of the gas is directly proportional to the pressure at constant temperature. So this is the another form of Boyle's law. Okay. Next let us discuss about the graphical representation of Boyle's law. Okay. Graphical representation of Boyle's law. So first one, Boyle's law, that is V is inversely proportional to P, or I can write P is inversely proportional to V. So first graph I need to draw between P versus 1 by V. Tell me, directly related, P is directly proportional to 1 by V. Okay, so the graph will be straight line passing through origin, this one. Is that clear? Next, if I need to draw the graph between P and V, they are inversely related. That means if we increase the pressure, then volume will be minimum, and it's vice versa. So the graph I am getting over here, a graph curve like this. This is a smooth curve will be obtained here. and since in this condition your temperature is constant, so this one is called isotherm because this graph is obtained at constant temperature. If temperature is constant, then it is called isotherm. Next, remember, with increase in temperature, here temperature is constant, so Boyle's equation, that is PV is equal to K. Okay, the product of pressure and volume always remains constant. So let us do another graph which is based on the equation PV is equal to K. PV is equal to K. Okay, so if I do a graph between this one is PV, product of pressure and volume, and here this one is, I can take pressure, or you can consider volume also, no problem. So the value of PV is always constant, whatever the value of pressure may be. If you increase the pressure, then gradually the volume decreases because it is inversely related. So if you increase pressure, then there will be decrease in volume, so that the product of pressure and volume always remains same. So the graph will be here. This one is at T1, and if high temperature is constant, if you increase the temperature, then definitely the volume factor becomes more, so the product becomes more, and the graph for PV will be over T2. Okay, so condition over here, T2 is greater than T1. So this is the graphical representation of Boyle's law. Clear? Students, now after the theoretical part of Boyle's law, let us discuss the numerical based on Boyle's law. That is, a vessel of 120 ml capacity contains a certain mass of a gas, that means mass of gas is constant, certain mass of a gas at 20 degrees centigrade and 750 mm pressure. That clear? The gas was transferred to a vessel whose volume is equal to 180 ml. Okay, so calculate the pressure of the gas at 20 degrees centigrade. That means temperature is constant. So here temperature is constant, so we can apply Boyle's law. Okay, by applying Boyle's law, we get P1 V1, that is equal to P2 into V2. Okay, so here you can consider this P1, that is given as 750 mm into volume, that is 120 ml, that is equal to, you have to calculate the pressure of the gas. Pressure of the gas means final pressure P2 will be how much, and volume V2, that is given as 180 ml. Okay, so very simple. So this P2 becomes equal to 750 into 120 divided by 180. So the answer that will coming here, can calculate. So pressure of the gas becomes 500 mm. 500 mm. Okay, so these are very easy numericals. So you have to concentrate the condition, which one is constant. So here temperature is constant, so you can apply Boyle's law. Okay, P1 V1 is equal to P2 V2 and calculate the answer. Clear? Next, a similar type of a question is there. 103 ml of CO2 were collected at 27 degrees centigrade. Okay, and 763 mm pressure. What will be the volume if the pressure is changed to 721 mm at the same temperature? So this condition is very important. At the same temperature means the condition is temperature again remains constant. Temperature is constant. Clear? So at given condition, first one, at given condition, that is V1 103 ml, P1 763 mm. Next one you have to calculate, that is you can write final condition. Okay, so that is pressure is changed to P2 721 mm and V2 you have to calculate. Now applying Boyle's law. Now applying Boyle's law. So what we will get? Boyle's law, P1 V1 that is equal to P2 V2. Okay, so apply the values. P1 763 into V1 103 that is equal to P2 721 into V2. Volume is asked, so V2 that is equal to 763 into 103 upon 721 that is equal to 109 ml. 109 ml. 109 ml. This one is the required volume. Okay. Students, another numerical is there. A balloon is filled with hydrogen at room temperature. It will burst if pressure exceeds 0.2 bar. If at 1 bar pressure the gas occupies 2.27 volume, up to what volume can the balloon be expanded? So this is the limited condition at which the balloon can be bursted whenever the pressure becomes more than that of 0.2 bar. So this is the limiting. So very easy concept is there. Again you can apply. Temperature is equal to constant. So P1 V1 is equal to P2 V2. So P1 is given to you. V2 you can calculate 0.2 into V2. P1 is given you 1 bar into 2.27. Okay, so likewise you can calculate V2, that will be coming out to be 11.35 liter. Okay, so this one is the limiting volume up to which the balloon can be filled up by the air. Okay, so today we have explained Boyle's law and graphical representation and the numerical based on Boyle's law. Okay.